Structure and function. They go hand in hand, don't they? Engineers prove to us again and again with their innovative creations that objects can be much more than the sum of their parts. To help make that point today, I built this model plane. Pretty cool, right? It has wings, a fuselage, tail fins, landing gear, propeller, all the structural elements necessary to make up a flying machine. But you probably already realized that this device is not going to fly. It's not going to interact with its environment the way that I want it to. Not because it lacks a particular structural part, but because those parts are not arranged in a very specific way. If my wings, fuselage, tail fins, and landing gear are arranged one way, I get flight. And another, who knows what I'm going to get, but it's not going to be flight. Molecules, it turns out, are no different. Their molecular formulas give us a recipe for how many of each atom must be present and how they're connected. But they fall short of giving us another critical piece of information: how those connected atoms are arranged in space. And just like in our example of planes, it turns out that when it comes to determining how molecules will behave, the geometric arrangement of their parts, in this case atoms, can be every bit as important as their identity and connectivity. Consider this: water and carbon dioxide, familiar materials to us all, both essential to life in many, many ways. Now, these are some of the simplest compounds possible, each consisting of just 3 atoms. Yet, water is found as a liquid at room temperature, and carbon dioxide is gas at all but the most frigid of temperatures. In fact, temperatures have to reach a chilly minus 82 degrees Celsius before carbon dioxide finally forms something other than a gas. That's a remarkable difference in properties for 2 small molecules with so many similarities. And why so different? Well, the answer to this question, just like our airplane example, lies not only in the number or identities of the component atoms, but in how they are connected. Today, we're going to discuss molecular geometries. Let's start simple. A molecule of O2, diatomic oxygen, is the allotrope of oxygen that we encounter most commonly here at the Earth's surface. It consists of 2 oxygen atoms connected by a double bond. With a defined average bond length and only 2 points, those defined by the oxygen atoms, there's really only one geometry that could possibly define this molecule: a straight line. Consider this: chemically inert nitrogen gas, highly toxic chlorine gas, and the powerful acid hydrochloric acid. All examples of simple diatomic molecules. Now, if I move one atom relative to the other in molecules like these, what happens? Of course, the molecule simply rotates. I may have changed its orientation in space, but I haven't changed the geometric relationship between the 2 atoms making each up. I'm simply making the molecule tumble. So, diatomic molecules can only take on one possible arrangement of atoms as a result of their simple makeup. If I try to move one of the atoms, I only succeed in rotating a linear construct. But let's take just a baby step forward and consider a molecule with 3 atoms. Let's look at water, in which a central oxygen atom is bonded to 2 hydrogen atoms for a total of 3 atoms per molecule. Now, the addition of that 3rd atom introduces a new wrinkle. If, just as before, I hold the molecule steady, but move one of the atoms, something changes. The 3 atoms have defined an angle, and that angle is altered when one atom moves relative to the others. Now, the Lewis structure of water is simple enough to construct, but when we try to translate that structure into a 3-dimensional molecule, we have to ask ourselves, are those 3 atoms all in a row? Or do they find themselves in a nonlinear orientation which defines an angle? And if so, what is that angle? All of these questions matter because, as we'll soon see, their answers will come to bear on the physical and chemical properties of compounds containing more than 2 atoms. The answer to the questions lie in the ideas of a few great researchers who put their faith in Gilbert Lewis using his 2-dimensional structures of atoms and simple molecules as a guide to create a theory that predicts the 3-dimensional structures of molecules. This theory is known as Vsepr theory, sometimes spoken as Vsepr theory. It's an acronym for valence shell electron pair repulsion theory. And this relatively simple theory represents one of the scientific community's first attempts to connect what was known about atomic structures to molecular structures. It's remarkably effective when applied to simple molecules like water, and still is often invoked in modern research. Vsepr theory hinges on a very important concept, the concept of electron domains. An electron domain is simply a concerted region of electron density in the valence shell of an atom. Now let's think about that. Where do we find regions of high electron density in the valence shell of an atom? Well, that would be in the orbitals holding lone pairs and in the orbitals forming bonds to other atoms. So a lone pair would constitute one electron domain, and so would a single bond to another atom. Now, double and triple bonds also each collectively represent a single electron domain, since all of the electrons involved in that bond are in close proximity to one another. Now, they share the same region of space, so they make up a single domain. To apply Vsepr theory to any small molecule, we simply focus on the central atom of the molecule and ask a few questions about its electron domains and how they push against one another. The first of these questions is, what is the Lewis structure for the molecule? We simply apply what we've already learned about how to construct a Lewis structure, and this helps us to determine the central atom and the connectivity of the other atoms in the molecule. So here are the Lewis structures for water and carbon dioxide as we previously determined them. Now the second question, how many electron domains are on the central atom? And finally, our third question, how can those electron domains best distance themselves from one another? Now there's actually a fourth question here, and that is, what sort of geometry do the electron domains create around the central atom? We call this an electron domain geometry. Once we have this, we can simply ignore the presence, but not the effects, of lone pair electrons, paying attention only to the atoms and the shape that they trace out. And this becomes the geometry that we see when we look at the molecule. So at this point, we've determined that molecules with 3 or more atoms can differ in the geometric arrangement of the atoms that make them up. But molecules can be much more complex than this, consisting of many atoms or groups of atoms, all bonded to a central atom. So first, let's consider all of the geometric possibilities that combining various elements of the periodic table has to offer. We could determine the geometry of every molecule known to man using Vsepr, but we're on a schedule here, so we're going to need to take a new tactic. And fortunately, we have one. We can condense the analysis down to just a few generic possibilities, using generic markers for central atoms, connected atoms, and lone pairs of electrons. See, when we consider most small molecules, specifically those with just one central atom to which all other atoms or groups of atoms in a compound are connected, we can create a generic table of geometric possibilities using a very simple notation. We'll define the central atom as A. All atoms or groups of atoms bonded to that central atom through the same electron domain will be called X. And all lone pair valence electrons on that central atom will be defined as E. So to start, let's limit our discussion to molecules with a central atom from the second row of the periodic table. When we use this notation, we find that molecules with central atoms from row 2, only being able to hold 8 valence electrons at most, only have 4 possible situations. We'll begin with the simplest possible example, 2 or 3 electron domains. Now, when we have 2 electron domains, there's really only one potential arrangement, and of course that's linear, which I've shown here, where the 2 domains are at opposition. This leads to only one type of potential molecule as well, right, in which the shape has the electron domains 180 degrees apart from one another. So this is the way the molecule would look if both of those bonded atoms are actually atoms and not just lone pair electrons. This leads to a generic formula of AX2E0, where the X represents bonded atoms, the E represents lone pair electrons, and the A, of course, represents the central atom. Now, we would call this molecular geometry linear because it mirrors the linear domain geometry. And an example of a molecule like this is carbon dioxide, just like the carbon dioxide that you're inhaling and exhaling right now. When we go up to 3, we find that we have what's called a trigonal planar electron domain geometry, in which all 3 of our domains are, again, as far apart as possible, which leads to an angle among them of about 120 degrees. But now there are 2 potential possibilities here as far as the shape of a molecule is concerned, and it depends upon how many atoms are bonded to that central atom. Let's go with the simplest example in which all 3 of the domains are bonds. We would call this molecule an AX3E0. And again, we would call the molecular geometry exactly the same name as we do the domain geometry. This is a trigonal planar molecule. And a classic example of this is boron trifluoride, a chemical reagent used by organic chemists. But if one of those domains is not a bonded atom, but rather a lone pair of electrons, remember, we still have a trigonal planar electron domain geometry. But we have to do our Jedi mind trick here, and we're not looking at these electrons. So the AX2E1 actually appears as a bent molecule, even though it's a trigonal planar electron domain. Now, a classic example of a bent molecule is ozone. This is one in which we have 3 electron domains, but only 2 of them are bonding. Let's step it up a little bit farther and look at 4 electron domains. In this case, we have a tetrahedral domain geometry. And in order to show it a little bit better, I'm going to turn it on its side here for you. So now we can see how those domains are all arranged around the central atom. Notice that the 3rd dimension has come into play now. So these angles are 109.5 degrees in an idealized tetrahedral shape. When all of those domains are bonded atoms, again, we have a formula that is AX4E0, corresponding to a molecular geometry that's exactly the same as the domain geometry, tetrahedral. An example of this being methane gas, which is found in natural gas. But if we start exchanging out those bonded atoms for lone pairs, the apparent geometry of the molecule starts to change. Here I have one domain that does not have a bonded atom. So this molecule would be an AX3E1. Now, if I do my Jedi mind trick one more time here, take those electrons away. Those aren't the electrons I'm looking for. I get a shape that looks a bit like a pyramid. So this would be called trigonal pyramidal, sometimes pronounced trigonal pyramidal. You'll hear it both ways. Example of a molecule that has this geometry is ammonia. But since we have 4 domains, we have one more possibility, and that is, what if 2 of those domains do not involve bonded atoms, but instead lone pairs? Well, now I have an AX2E2 molecule, and when I erase those electron pairs, but not their effect, I see, again, a bent molecule, but this time with different angles. And a classic example of a bent AX2E2 molecule is water. The row 2 elements are limited by the fact that their valence shell can only hold 8 electrons at most. Only the geometries that we just looked at are possible. Absolutely no exceptions. End of story. But what happens when we use a different central atom, one from row 3 or beyond? Elements from the 3rd row and beyond have the ability to hold more than 8 valence electrons because they have a nearby d sublevel available. In most cases, this allows 1 or 2 additional pairs of electrons to be on the central atom in an apparent violation of the octet rule. Carrying on, let's look at 5 electron domains. In this case, the electron domain geometry is what we call trigonal bipyramidal or trigonal bipyramidal. And something interesting happens here when we have 5 domains, and that is that not all of those domains are identical. We have a bond angle here that's obviously 90 degrees, but if I turn it just a bit, you'll notice that there are different bond angles here. There are also atoms that have a 120 degree bond angle, so they're chemically distinct from one another. We call these 2 positions here at the top and bottom, as I've oriented it, we call these axial positions. And those 3 that are around the center here we call equatorial positions. So now I have to think a little bit more carefully when I start building molecules about whether bonded atoms or lone pairs will make their way into axial or equatorial positions. Let's do that. Of course, the simplest possible shape is one in which we have all of our domains as bonded atoms. That leads to an AX5E0 formula. and a molecular geometry that's the same as the domain. An example of a molecule that's trigonal bipyramidal is phosphorus pentafluoride, a drying agent used in the lab. But if we change one of those out and give ourselves one lone pair that is not involved in a bonded atom, we get an AX4E1 formula and a molecular geometry that looks a bit like a seesaw. So that's what we call it. This is a seesaw molecular geometry. And an example of this is sulfur tetrafluoride. Let's go one step further and take away one more bonded atom and replace it with a lone pair. So in this case, we're dealing with an AX3E2. And the AX3E2, when we remove those electrons that are not involved in bonding, looks an awful lot like the letter T. And in fact, that's what we call it. This is a T-shaped molecule. An example of a T-shaped molecule is the interhalogen compound chlorine trifluoride. Let's take it one step further now, go up to 6 electron domains. This will be our last one. When we have 6 electron domains, Vsepr theory tells us that the bonded atoms will be, or the domains rather, will be as far apart as possible from one another, meaning that they'll take on angles of 90 degrees throughout. So when I tilt this molecule on its side, we can see clearly that every bond angle between every atom in this molecule is 90 degrees. So now we don't have to worry about equatorial and axial positions anymore. We can simply think about where the electron pairs are going to go and what kind of shape they're going to make. Now, when all of those domains are bonded atoms, again, my shape is going to be exactly the same as my domain geometry. So an AX6E0 corresponds to an octahedral molecular geometry. Now, remember, we call it octahedral even though there are 6 bonded atoms, because when we trace out lines among all the atoms, it creates the shape of an octahedron. And an example of a compound like this is sulfur hexafluoride, a very, very dense gas that's sometimes used as an electrical insulator. Removing one of those bonded atoms and replacing it with a lone pair leads to an AX5E1 formula. And when we remove that lone pair, but not its effects, we see a shape that looks a lot like a pyramid with a square base this time. So we call AX5E1 molecules square pyramidal or square pyramidal. An example of this is another interhalogen compound. This is bromine pentafluoride. Let's take one more away, but let's think about where we're going to take it away from, because now that I've removed one, removing the second, I have 2 potential locations, either next to it or at opposition to it. Now, when I take away that second bonded atom, I take it away from the opposing location, right? It's not one of these adjacents, it's one right up here on the top, as far apart as possible. And this gives the lone pair electrons as much space as possible, because remember, they like their space. So when I do this and then remove the appearance but not the effects of those lone pair electrons, I get an AX4E2 molecule with a geometry that is planar, but it's got 4 points, so we call it square planar. An example of a square planar molecule is xenon tetrafluoride. So applying Vsepr theory allows us to explain and even predict the geometric arrangement of atoms in relatively simple molecules. Understanding molecular geometries also helps us to predict and understand some of the most fundamental properties of everyday materials, like water and carbon dioxide. Think about these 2 compounds once more. Water, commonly found as a liquid capable of dissolving a variety of salts that form ions in solution. Water only boils at 100 degrees centigrade, right? Now, you see the polar covalent OH bonds in water each have a partial charge separation. And the fact that water is an AX2E2 molecule means that it has this bent geometry. This means the molecule itself has a more positive region down here and a more negative region up here in its overall electron cloud. Now, if the OH bonds instead pointed in opposite directions, their dipoles would cancel over the molecule. But they don't. Now, take a look at carbon dioxide. Its polar carbon-oxygen double bonds are aligned opposite to one another. Now, this means that they cancel, and overall, there is no net molecular dipole in CO2. So, water is a polar molecule, and CO2 is a nonpolar molecule. And we know this from their molecular geometries, right? So, why is that so important? Well, molecules with strong permanent dipoles can align themselves so that the dipole of one molecule interacts favorably with the dipole of a neighbor. Now, we'll explore this effect in greater detail in our lecture on phase changes, but for now, the important connection to make here is that just like magnetic dipoles and magnets can make them prone to sticking together, the electrostatic dipole of polar molecules can cause them to stick together better when aligned properly. It's this ability of water molecules to attract one another and stick together that gives it the ability to remain liquid or solid at the temperatures necessary for life. If water were instead linear, having no dipole at all, it would probably have properties more closely resembling carbon dioxide, which, just like water, contains 3 atoms with 2 highly polar bonds joining them, but it's a gas at all but the most frigid of temperatures, and even when liquefied, can't dissolve salts the way that water can. So this simple geometric feature, a slight bend in the water molecule, is all that stands between a planet like ours being covered by oceans and glaciers and one in which water would most likely only be found in the atmosphere, if at all. It would be a radically different environment, all caused by one simple bend in one of the simplest molecules that we can imagine. Now, we can use this technique to analyze the polarity of just about any small molecule that we want. First, determining the electron domain geometry, then the molecular geometry of the molecule, and then finally considering if the individual bond dipoles within that molecule cancel out or not. So let's review. In this lecture, we asked a new question about molecules. Not how are the atoms connected to one another, but rather how are those atoms arranged in space around one another. We saw how Vsepr theory assumes that lone pairs and groups of bonding electrons want as much space as they can get around the central atom of a small molecule, causing them to spread out. And this makes them take on consistent, predictable electron domain geometries about that central atom. We saw how chemists use the shape created by tracing out electron domains of a molecule to determine what's known as its electron domain geometry. And these include linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Next, we saw how mentally removing any lone pairs from the electron domain geometry, but leaving their effects in place, allows us to determine the molecular geometry of a molecule. And this included new geometries like trigonal pyramidal, seesaw, T-shaped, square pyramidal, and square planar. And finally, we saw how important understanding molecular geometries can be. But as dazzling a job as Vsepr theory does in describing the geometries and behaviors of the compounds we looked at today, it falls short of answering some fundamental questions about the bonds that hold molecules together. For example, why are there 2 different positions in trigonal bipyramidal systems? And why are all 4 bonds in methane molecules perfectly identical? Our next task is going to be to try to answer a few of these questions that Vsepr theory has left unanswered. The next time we meet, one of the fathers of modern physical chemistry will be with us, Linus Pauling, and we'll discuss his theory called orbital hybridization. It's time for another challenge problem, one that's going to help us exercise the skills we've learned over the last 2 lectures. So here it is. Which of the following molecules are polar? CCl4, CS2, SO2, and ClF3. If you'd like to solve the problem for yourself, you can pause now, and I'll be right here when you get back to give you the answer. Okay, ready? Here we go. Now remember, asking if a molecule is polar is a deceptively short-worded question. It requires us to figure out a number of things in progression as we go. Specifically, we've got to go through all of these steps to get there. We've got to first figure out the Lewis structure, which requires that we count valence electrons. From there, we can use the number of electron domains to get the domain geometry. From there, we can get our generic formula and molecular geometry, which will finally allow us to analyze how the dipoles within these molecules are arranged, just like we did with carbon dioxide and water, to finally answer the question, is this molecule polar? Let's start with CCl4. carbon tetrachloride. This molecule has 32 valence electrons, and carbon is the least electronegative element, so it'll go in the center. And when I create the Lewis structure, I find that I have a carbon with 4 sigma bonds and no lone pairs. This means that it will have 4 electron domains, creating a tetrahedral electron domain geometry. Its generic formula will be AX4E0, and its molecular geometry, therefore, will be tetrahedral. Now, when we take a tetrahedral structure and analyze the bond dipoles within it, notice that they're all pointing at the 4 corners of a tetrahedron. So in this case, if we're using CCl4, in which all 4 of these dipoles are of equal magnitude, we expect them all to cancel out. Their vector sum is a point. That means that CCl4 is not polar. There's no molecular dipole in this compound. Now let's apply that logic to the remaining 3 compounds and see what we get. In the case of CS2, we find that we have an AX2E0 compound. That means it's a linear molecule, and because the 2 CS bonds are equal but opposite, they also add up to a point, creating no molecular dipole. This is not a polar molecule. SO2, on the other hand, notice that SO2 has got a lone pair of electrons in addition to the 2 bonding domains. So this is an AX2E1 molecule, which means that it's going to have a bent molecular geometry with a 120-degree angle between the 2 bonds. Now, when we look at those dipoles, notice that they don't cancel out perfectly. When we add those 2 vectors together, we actually get a net molecular dipole here pointed straight downward. That means SO2 is in fact a polar molecule. Finally, ClF3. In this case, my Lewis structure tells me there are 5 domains, so this is a trigonal bipyramidal domain geometry, and an AX3E2 molecule, which means it has a T-shaped molecular geometry. Placing my carbon-fluorine dipoles in with that geometry and adding them together, I see that these 2 dipoles here and here will cancel, but that this one here has no other dipole acting in an opposite direction. In other words, there will be a net molecular dipole in this orientation. ClF3 is in fact polar as well.